Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
This problem deals with calculating the speed needed to have a charged particle hit a target as it follows circular motion in a uniform magnetic field. So what we're given is a coordinate system, something like this. And everywhere in this space, we have a magnetic field that is heading into the screen. So I'll draw it like this, and it's everywhere, not just that location. So we'll just remember that. And we have a charged particle. I'll use a little purple thing here. Positively charged proton here. And it's sitting there with the charge plus E. Now, we're asked to figure out what's the speed that's needed for this particle to have such that it's going to hit a target that is at negative 0.1 meters in the x direction and negative 0.10 meters in the y direction. Now, because of the magnetic forces involved, the only way to get this proton here to hit this target is to have it shoot it either directly vertically, so along the positive y direction, or along the negative x direction. So if we launch this particle initially vertically upward, right, we're going to have from our right-hand rule, we're going to have a magnetic force to the left, and our circular motion is going to look something like this. So we're going to come around like this, come around and hit there like that. And if our goal is to hit, and the reason I drew the circle like this is because our goal eventually in this problem is to hit this target. So I needed to include that negative 0.1 location in the trajectory of my circular motion. Now, my particle can also be launched this way and create a circular path that also includes that. So it looks a little bit like a oval, meant to be a circle there. A circular path that also can have our proton hit the target there. So the question is, if I do want my proton to hit the target, what is the velocity I need? Well, we know an equation for the circular motion of a charged particle in a magnetic field, right? It's m times v, so the momentum of our charged particle, divided by the absolute value of the charge value, multiplied by the magnitude of the magnetic field that the charge is moving around in. So you'll see from our diagram that if we want to hit the target at either of these, at that location of negative 0.1, negative 0.1, we'll have to map out a circular path that includes that target, and we'll see that the radius of our circle, if we measure that out, right, the radius of the circle is just equal to that 0.1 meter. Well, maybe I shouldn't have it equal to negative 0.1, right, but these radii here that we have for our circles, that is going to be 0.1 meters, right? So we actually know the size of the circle we need to have this this proton hit the target. So I want to figure out the speed I need to make that happen. Well, I know everything else. I know the mass of my proton. I know the magnetic field through which it's traveling. I know the charge of a proton. I just need to find its speed. And I just figured out the size of the circular paths that it travels. So I solve for v. I get an expression of the magnitude of the charge times the magnetic field times this how large the radius is of our circular path divided by the mass of our proton. So we plug in everything we know. What's the charge of a proton? The elementary charge, 1.6 times 10 to the negative 19 coulombs. Magnitude of the magnetic field through which this is traveling is given as 0.010 teslas. How big is our radius of our circle? 0.1 meters. And then we're going to divide that all by the mass of a proton, 1.67 times 10 to the negative 27 kilograms. Put that all in our calculator, and in the end, we see that the speed we need in order to have the circular path of this proton intersect with that target at negative 1,1 is about 9.6 times 10 to the 4 meters per second. So, quite fast.